Rick, welcome to the Real Talk.
Hey.
I'm so fortunate to have you here. Thank you for joining us. And as you know, tell the audience how I came upon you is through a little webinar thing you're going through BWG talking about supply chain. I'm like, wow. I'm like, who's this Rick Reigel? He has so informative stuff, so much knowledge. I'm gonna get to him. And I got into GaN Systems. I'm like, oh wow, this industry is what's going on, and I'm really happy to have you here today.
Well, thanks, Rob. I really appreciate the invitation to come here, and especially to be here in person. This is actually my first time out of the house in over a year, and wearing a suit. So it feels good to be here.
Feels
live
good.
today.
Yeah, that's good. I mean, as I said,
Better.
so how? I mean, let's set a thing aside with business-wise. How are things? How are things from the last year? Just like you said, how are things going from personal business-wise? Did you say coming out of the house or office or work from home? How is that working?
It's been an interesting year of learning and transitioning to more of a virtual sales approach. I'm a salesman. I appreciate talking to customers and learning from them firsthand, and understanding, body language is a big part of communication.
Yes.
And what you can learn. It's a little easier in person to get real concrete information to take action on.
Yeah.
People are a little more shy when they're in front of a camera.
Yeah, I agree. I think the camera has exposed a lot in the last year because a lot of people, but it's always, I tell my staff and my team, like, hey, it's this, you look the same walking into a meeting or being on camera. It's the same person. It's just through, but people, that lens right there sometimes creates a lot of fear and anxiety, but I'm great. At least it's good to hear that one of your first in-person things are coming onto the Real Talk and really talking about GaN Systems and your history, what's going on. But I'd like to first start, who is Rick Reigel? And tell us a little about your history, how you got here.
Okay.
Yeah.
Well, I'm born and raised in Southern California, here in Orange County. I'm a native. Graduated high school and went to the University of California, San Diego, where I got a degree in electrical engineering. I also picked up a minor in geophysics.
Oh, wow, okay.
It's actually, there's some related theories in the physics world there. Afterwards, I picked up along the way going to night school an MBA from Pepperdine, which was also has a local campus here. And so in my personal life, I'm very active, very balanced. I played a lot of competitive sports growing up as a kid and through high school, and today really enjoy, surfing, warm water, skiing, cold powder, hiking, biking, a little bit of golf here and there when time permits, and just generally being outdoors in the great environment that we're in.
Oh, I love it. I mean, I think we share a lot of similarities. I'm an OC born and raised, but all those hobbies and all the outdoors and water, surfing, snow, hike, just things like that. We're very fortunate. I think Southern California has the climate that's all year round for it. But of course, the last year has thrown a little wrench in all our activities. But overall, that's good. I mean, it's good to see, because I remember our first discussion we had, I saw your surfboards and starting from there and how you got into engineering. So engineering, what it was, how did you get an engineer? What was,
I originally wanted to do something that had an impact in the world, and I thought I would be a doctor. And then when I got into college and started learning more about it, learned that I was maybe perhaps a little squeamish with all of the human anatomy and inner workings and things, and then quickly decided that the better route for me would be something more technical on the engineering side. And so I took the electrical engineering degree in communication systems and microprocessors was my specialty. And that led me to an opportunity right out of college into a company called Burroughs.
Burroughs, okay.
Burroughs, which became Unisys.
Oh, right.
Today.
Okay.
That was in the era of the mainframe computers. And so I did that for 4 or 5 years as a design engineer, and got a lot of questions. My wife tries to help me to dress for success. So I was looking good. A lot of the guys would be like, "Oh, who's the new salesman?" or "Who's the new marketing guy?"
Yeah.
No, I'm an engineer. Oh, well, you should really be in sales. And I got that pressure, and I met a lot of the vendors, and through some of the vendors, I established relationships. And so I changed from an engineering specific career to a field application engineering career, and was hired by Advanced Micro Devices.
Okay, AMD.
AMD, tremendous company. This was in the era of heavy competition with Intel in the 80s. The PC was just coming about. So that was exciting, and I worked there for a few years as an FAE, and then slowly through the ranks of sales, and into sales management, and was running the western half of the country in 2002. And that was a big change, a lot of inflection in the world in 2001, 2002. The semiconductor world had just come off of the Y2K boom bust cycle, and so everything changed. And I looked around. I think AMD was struggling a little bit at the time. They're doing tremendous today, it seems. And so I had to look around and reinvent myself.
Yeah.
And I wanted to stay here close to my roots in Southern California. Had some opportunities and talked to Broadcom, but I ultimately decided to change totally and go into power electronics.
Yep. Okay.
And we'll talk more about some of what that has led to. But so I joined International Rectifier, which is just up the road in El Segundo in LA. And I worked at IR for 11 and a half years, again, progressing through various steps of sales, and ultimately was vice president of sales at IR when we were acquired by Infineon in 2015.
How was that shift?
So that was an interesting shift. I mean, IR was one of the oldest semiconductor companies, the pioneer of the MOSFET. And Infineon was a newer spin-out of Siemens, but they had grown tremendously rapidly, had great technology, great leadership program. They had actually outgrown IR to the point where they acquired it, but it was a completely different culture. They had 6 vice presidents doing the job that I was doing. So the discussions were, well, we have 6 people that do what you do. We're not really sure what to do with you yet, but stick around for a year through the transition, and we'll see what happens. And then turns out at the end of that year, they did find a role for me, and I ran the regional and channel sales group for the Americas for 4 years.
Oh, wow. That's fascinating. So that IR, and I know that we discussed a little story about the beginning of, I think the early 2010, 2012 was with the Tesla. So you were tell us a little story about how you were involved with Tesla on the Model S and how you designed the MOSFETs in.
Absolutely. So that was one of the 2 biggest accomplishments in my sales career. So the Model S came about. They had actually acquired a traction drive from a small company in San Dimas, and I had worked with and had familiarity with them. But it was very early on, and the technology they used wasn't a precise fit. They had to use a lot of semiconductor switches, IGBTs in parallel, and they weren't good at matching. And so my first experience with Tesla was to go tell them that the design that they had acquired, while it worked for small volume production, was going to be problematic for very high volume, like I knew they wanted to go. And I actually had to design out our part and try to design in new technology.
Oh, wow.
You can imagine they didn't like that very much.
So we're at that level, at that size, there was still startup. Did you work with Elon? Did you work with Elon?
There was maybe 30 people in a small garage bay. Kind of an operation, and they slowly took over each and every bay. But yes, I got to meet Elon, JB Struble, some of the other early engineers, all the founders early on. And again, wasn't so pleasant because I was the messenger sent by the company
to make some changes.
And so that didn't go well. But it was a story of perseverance because the technology that we introduced to them, ultimately, they went to some of my competitors. They ended up coming back to me 2 years later, and we got into the Model S.
Oh, wow.
And really enabled the Model S sport mode and ludicrous mode and some of those things that require cutting-edge, high power to achieve.
So that's fascinating. So you're directly involved with all those the steps, the Model S, evolution of the Model S.
Indirectly, I mean, it takes a team. They were a great set of engineers, and Elon's a great leader. He would just throw the challenge out in front of the engineers, and they'd go make it happen. I was leading the team at IR that helped them to achieve the optimal product for what they needed to do at the time. We were later rewarded in 2013 with a Development Partner of Excellence award from Elon directly, and a nice dinner. We had early access to the Model X at the time. So that was a lot of fun. It was a great accomplishment. And my biggest competitors were all sitting in that audience at that meeting, and I can't help but think one of them, Infineon, took notice that this company IR had won one of the most important designs in recent history, I think.
Yeah, I mean, that's the start of evolution of the EV. I mean, as we know, Tesla has changed the world and has pushed everybody to move forward, not with just EV, but battery technology, solar, all the stuff to go into that world of renewable energy and especially battery power. So that's fascinating. That's an achievement. That's something to put in. I remember you have that Model S on your run. You're driving a Model S too. Those are your two things because you had the picture of it.
Yes.
Yeah, on your wall by it, and that's fantastic. That's great. So now it leads us to after leaving Infineon. So did you from there? You went? Is this?
So
Where'd
worked
you go?
at Infineon. It was a great run for 5 years. A lot of amazing, smart people. Strong business acumen, but it was a very big company and one that required a lot of travel. I was in Germany every other month and perhaps not liking the quality of life I had and wanted to do something different. And I found a small startup company called GaN Systems that was on the verge of breaking out and achieving real growth and just need to accelerate the sales challenges.
Oh, wow.
And so I had been exposed to that technology at IR and Infineon, so I knew a little bit about it and knew their reputation and the product very strong. They are today still, we are the leader in gallium nitride sales. So
tell us a little about GaN Systems. How did it start, as you say, start up and where they are from past, present, and the future ahead? What's going on with GaNs? What's the system? Gallium nitride is a real used wide term today. But really, what is the emphasis of GaNs and what are they trying to, what's their mission?
So really, I think it goes back and it's rooted in the power semiconductor switch. And if you understand the history of that, International Rectifier invented them back in the late 70s, early 80s, commercialized it, licensed the patent out to a broad number of companies. And that really drove the first revolution of miniaturization of power electronics, which enabled computers to move from mainframes to desktop. And then ultimately, the advancements in MOSFET technology over the years led to the miniaturization of a lot of power electronics. Gallium nitride is just the next evolution of the semiconductor switch. And what's happened over this 30 years of constant improvement, the MOSFET switch is ubiquitous in all these power converters. It's got some limitations in terms of the physics in silicon. Its resistance is what determines the overall efficiency in the system. So less resistance is better. But in order to make less resistance, you either need to make a bigger die if you're doing a lateral device, or you need to move vertically. And so the industry moved from lateral to vertical power semiconductors over that time. But then you still run into a physical limitation because the resistance is then the height, the thickness of the material. And the semiconductor companies have been able to manufacture very thin wafer down to 40, 50 micron thick. So it's essentially a piece of glass, but with the consistency of a tissue paper. So you can imagine there's a limit to how far you can thin that down and shrink it, which means improvements in MOSFETs and IGBTs have become asymptotically flat over the past few years. It takes a lot of investment to get 0.1% better efficiency out of it. So about a decade ago, the world started looking at what comes next. And they started looking at various so-called wide bandgap materials, of which gallium nitride is one, silicon carbide is one, and there are others. And today, a decade later, both silicon carbide and gallium nitride are finding their way into commercial applications, not just science projects any longer.
Yeah, I mean, it's fascinating as I've done the research on it too, because I know that gallium nitride was first started with some of the LEDs.
It started in LEDs.
Yes.
There's been pure gallium nitride transistors for quite some time, but the key differentiator here is the substrate. If you buy a gallium nitride substrate, the best you can buy is 2, 3, 4 inch wafer equipment. As you know, wafers have gotten much larger in the silicon world. And so the state-of-the-art approach is to take a silicon wafer, which are ubiquitous, a 6-inch wafer, and grow a layer of gallium nitride on top of the silicon. So you get the cost advantage of the silicon infrastructure. You grow the gallium nitride later, which is where the switch happens. And so you get the best of both worlds of ubiquitous supply of silicon wafers at low cost, mature cost, and the gallium nitride switch. That's contrasted to silicon carbide, which is a pure silicon carbide process to grow the boule and to slice wafers out of that and make silicon carbide transistors. Both of these are wide bandgap. They switch very fast.
Yes,
they have all the desirable features that they get away from the limitations on the on resistance that exist in MOSFETs. And there's another component too. So the on resistance is one component. The other is the switching loss.
So
Power
loss.
electronics switch on and off. So you have
Correct.
two components,
The
the
DC,
resistive
AC,
loss and the capacitive loss. And one of the benefits of gallium nitride is the switching losses are almost non-existent. There's very low losses. So this combination makes it a very desirable product. But with these technologies, why did it take time? For any new technology, you have to really prove three major things. You have to get volume supply,
The
not
scaling.
just science
Scale,
projects.
yeah.
You have to have, so you have to have the capacity. You have to get the cost down to where it makes sense, and you have to demonstrate reliability. And so those three challenges took some time to evolve to the point to where it is today. And I'm happy to say that in 2019 and 2020, the market for gallium nitride transistors has really taken off. So a lot of adoption.
And I've seen the GaNs is no, because it's fascinating that GaN Systems itself, a startup, got the name.
Yeah.
Right, because there are other companies out there that are in the same field, like Cambridge and some other companies doing these type of things with gallium nitride and getting in there. And GaN's got the Systems has the name, and it's very fascinating of that, because of course there's like, is it a company or is it just having GaN? But no, it's focused on GaNs and switching power supply. So what are all the? I mean, you have some on the table right here. You're showing us some basic power supply units for computing for basic say a laptop compared to the size.
This
diameter.
is the power supply out of my Lenovo laptop. It's 65 watts. It's pretty nice and small compared to where these things were 5 or 10 years ago. This is based on MOSFETs, but it's really at the limit of what you can do in terms of power density. You can see how big it is.
Correct.
This is a 65 watt power adapter based on GaN. And so
That's
you can
about
see from every dimension, it's about 30 to 40% less,
close to
less
half
volume.
the size. Yeah, volume.
It does the same job, and it does the job more efficiently. And why carry that around? I can't really put that in my pocket too easily.
Yeah.
This can power my laptop. It can charge my phone and go right in my pocket. So this, I think, analogy is great in the laptop and phone world. If you think about all the other electronics, whether you're in one of the data center segments or in a big EV, you have battery chargers in the EV. Correct. It's a much bigger unit, higher power, but the same analogy applies. With gallium nitride, you can make it smaller, lighter, more efficient, all of which are desirable things if you're driving around with it all day, because it can extend the range of your battery or make the car faster.
Yeah, so the form factors in general, for some of your audience even listening, is the form factor is, I would say, half the size, which allows to even have more circuitry for other things on the board, for the power or for the switching power supply. So right now, what are the industries that you guys are, with this type of technology, that you guys are targeting getting into?
So, so first of all, now that we've demonstrated the reliability and the cost by going beyond JEDEC qualifications and really taking it to automotive level qualifications, we had to demonstrate the reliability. The cost had to come down, which means the yields and everything had to come up. So over the past decade, that's happened. And it's really enabling now 5 key segments for us that are very high volume. The first is in consumer electronics. Exactly the products that we see here. It started in 2019 with aftermarket adapters, 2019 and 2020. 2021 is going to be the year where you see a lot of OEM in the box adapters coming out based on gallium nitride. And then the other consumer product where we see a lot of early adoption is in Class D audio amplifiers. It turns out there's a 5th benefit from gallium nitride, and that it's very low noise and creates a very pure sound, very low harmonic distortion amplifier, also reducing size and weight because you don't need as much heat sinking and things like that. So, so those 2 segments have been the first to really take off in volume. And consumer electronics is certainly a major trend in the world today, and miniaturization and efficiency are key. But there's 4 other segments where gallium nitride plays. The data center, the power that goes into a data center, and data centers are slowly becoming more and more of power consumption on the grid in the world. And so they're getting more and more attention to increase the rack space and the cost effectiveness of their data servers. And what the gallium nitride allows is, again, with a smaller power supply, that leaves more room in their rack in the server to include either more memory or more CPU units or other things and take up less space. At the same time, reducing the operating costs.
Yeah, operating costs. I think from what I've researched and read is not just the form factor; it's the energy, the efficiency of saving energy, being able to, as I said, expand form factor, smaller data center, or putting more, say, servers in a data center. About 20 to 30% more energy and more efficient, so less energy used. Correct. And I would say the weight's lighter, the lower cost of systems. These are things. Everything it adds up. That's one thing that I really mean is the shift in power electronics.
And it's not just data centers. Data centers is one good example. Another good one that's happening real time in the world is 5G.
Yeah.
And if you know a little bit about 5G, it's a higher bandwidth. Well, it requires higher power. Higher power in at the same time more base stations because the signals don't go as far. So you need 5 times as many base stations to cover the same area with the highest bandwidth. But you don't want the power supply that goes up the telephone pole or at the central office to become so large that it's unwieldy for the crews installing it. So they want to shrink the size of the power supply as well. So GaN is finding its way into the power infrastructure for 5G.
It's 5G. It's fascinating because the reliability, it has high reliability and environmental. Like I think the temperature, I think what silicon, basic silicon is about 100 C. It's a good highest, basic operating temperature below that. But I think gallium could go up to 300 C.
It can handle pretty high temperatures. The switching frequencies are very high. And so, yes, and because it wastes less heat, it's a more efficient semiconductor switch. You have less heat to dissipate in your box, which means you can shrink the size of it and reduce the amount of heat sinking and things like
cooling.
That
the cooling.
It needs to keep it at the reliable temperature.
So, and that comes to the cooling. I know there's a lot of water-cooled systems. Data centers have water cooling and then air-cooled. So that does also change that they can kind of not focus so much on water-cooled systems that they can actually use air-cooled because it runs at a higher reliability at a higher temp. Is that correct? Or
it's that's not so different than silicon in terms of the temperature. It definitely, though, because you're generating less heat, you can reduce the size of that system.
All right.
Depending on the power levels, you can't totally eliminate. You have to get the heat out. But for example, this little block right here has 4 gallium nitride switches on it. It's on a aluminum substrate circuit board. That can switch 3 kilowatt.
3 kilowatts.
Yeah.
That would probably probably be 3 times the size of a regular.
Exactly. The same analogy.
Same analogy here. Wow.
So you can imagine that when engineers see this, they get very excited.
This as people who are listening or even watching, this just fits in the palm of your hand compared to something that would take over your hand as a regular. Oh, wow. It's extremely fascinating.
Yep.
And the chip size and it is. The technology, as just like you said, is we're using more and more technology. Everything's connected and everything needs power. At the end of the day,
everything does. And so in my career, I was blessed to live through the decade of the mainframe, right, at the dying years of that. And the 90s became the decade of the personal computer. In the 2000s, it became about connected computers and smartphones and the internet. And each one of those trends drove semiconductor technology. Right. It drove Moore's law on the computation side, it drove the communication stuff, and it drove a miniaturization of power. Today, we're lucky enough to live in a world where we have 5 mega trends happening at the same time. We talked about the consumer electronics. We talked a little bit about data centers. But there's a huge boom in renewable energy, in solar and wind, in energy storage subsystems, batteries to be off-grid and to store things when the wind isn't blowing and the sun isn't shining. In addition, there's the EVs, which we've touched on. So you can imagine there's huge interest in a vehicle. Anytime something moves, size, weight, and efficiency are key to them. And so reducing that is a benefit, and that trend's tremendous. And then there's the industrialization and automation and electronification of motors in general that you find around you, you maybe don't think about in your
drives, motor drives,
your air conditioning and fan units to blow hot or cold air around. All the industrialization in factories and things are also becoming electronified and inverterized at the same time. And so these 5 key areas are driving all semiconductor growth, but they're areas where GaN can play very well and enable, and they're each maturing at various steps over the next few years.
Yeah, I mean, you hit that topic of inverter, as some people might even, the engineers and people understand inverting, but inverting, taking power from 110, 220, 240, and taking it down, or from DC-DC, AC-DC. There's a lot of loss in there's inefficiencies in that with silicon, correct? So
that's correct.
Yeah.
And like we discussed earlier, MOSFETs and IGBTs have gotten kind of the physical limit. Where it's very difficult to make big improvements, whereas gallium nitride is in its infancy and still has another 10, 20, 30 years of learning and continue to get even better. Yeah.
So for that, coming forward from that, so what are the areas for GaN systems right now? Where are your success stories and some of the case studies that you guys have done with some of your partners designed in for some of the products?
So there's many of them out there that are on our website that you can go see firsthand in each one of those segments. There are many more that we can't talk about. Even in some segments that you wouldn't think would be early adopters. There's this whole segment of new space, communication satellites, and other things where they can use commercial products. And it turns out that GaN is 3 times more radiation tolerant than silicon or silicon carbide. And so that has been an early adopter, and there's a lot of interest in new space, and there's even interest in the old space where they need very, very high reliability on very long missions. And I wish I could share more details.
No, that's fine. I mean, I would understand. People understand it'd be over to the aerospace, military. These are things that more technical, but those, because the most high reliability, longevity of life, power, efficiency of power conversion. There's a lot of applications for that.
Size and weight and efficiency are key in all of those applications.
Yeah,
it's moving very fast. So the weight is key, right? Every ounce, every gram.
Yeah, I mean, right now with power, even Southern California, as we do have a good infrastructure here, but as more homes, more things are built, we're getting limited on just the way of power, and then now a lot of people going to solar. And with solar costs coming down year over year, and we're getting more efficient on that, but gallium nitride could be a big, to scale, can help that for the efficiency of solar conversion.
Absolutely, right? And when you think about your solar today, you have your solar panels, which generates a DC voltage and current. You need to convert that into AC to use it in your house. And it's called an inverter, a solar inverter. Silicon has been used in that for quite some time now. We're starting to see gallium nitride adopted, and you would think that going from 94% efficiency to 96% doesn't sound like much, but if you look at it from the opposite side, the losses go from 6% to 4%. That's a 35% improvement in the loss. Now, if you add a storage system, a battery to your inverter, you go one pass through the inverter to get into the battery, another pass to get out. That's 2% plus 2%. So the overall efficiency is 4% better. That's a huge savings in terms of the overall system. And it's just at the beginning of that.
So it's just streamlining. I mean, the touch, again, it's funny, as you say, it's touch points. How many places touch, how much power is transferred, and kind of streamlining that. So on both sides, there's less energy loss, which, or you said, it could be up to 35%. Well, it probably can get greater over time scalability of the technology.
Correct. And you can certainly do things with silicon to achieve that as well. But at some point, it becomes a cost trade-off. And that's the key in everybody's mind when they're designing a product at the end of the day. Efficiency is one thing, but overall cost is bearing in that as well. And so if things become so complicated that it's too costly to do it with silicon, then GaN becomes a good choice.
That's one thing of silicon. I've talking about CPUs or now GPUs that because gaming or a lot of hype data centers and gaming, especially with building chips. So how, that's what I want to know from myself is a question for you is gallium nitride getting into full microprocessing units is for computing power? or for graphics processing units?
Not today.
Not today. Okay.
We are certainly involved with powering.
Powering them.
Those kind of things, DC to DC converters and so forth. But gallium nitride is a power switch. It's really one transistor in the package, where those others are millions of transistors on a die.
Okay. So that's why I wanted to understand, to clarify, because some people listen, it's like, how would that be different than, then can we use gallium to put it into CPUs or transistors? But you're saying it doesn't have the millions of transistors.
Not today.
Yeah,
I'm not going to say that it can't or won't in the future. Those things are still evolving, and logic processes are evolving.
Correct.
In gallium nitride, more for the analog side, gate drivers and temperature sense and other things like that current sense that go along with the power application.
Correct. So from this point, as also leading, what other options, it's a transfer of power between, I would say, the photons and the power that goes through it. But right now, what on your end, what do you see as, the future of it? Because the scalability, I think it's also the yield rate, because how to build a gallium nitride, go into, say, fab houses, or to build, because you guys, as a GaN system, what does GaNs, let's take a step back here. GaNs has a technology, has a system, and you guys partner up with packaging houses, or how does this work?
Yeah, so we're a fabless company.
Okay.
We outsource, and we partnered with the largest outsource.
The big guys, Global Foundry, TSMC,
and we have worked very close partnership with them to co-develop a process and to qualify it. And to work the iterations on the product since 2014.
All right, okay.
To get it to the point where 5 years later, we qualified it for production in 2019, meeting all of the JEDEC and automotive standards and going way beyond that. That was a big accomplishment, because it wasn't always easy early on. And we talked about the 3 keys to commercialization: volume, capacity, cost, and reliability. The reliability one is not one to be understated. That took a lot of work and a lot of close cooperation, and not just with the fab house, but with some of our strategic customers, who also through this became investors in GaN Systems. So BMW, Toyota, Delta Electronics are all strategic investors in GaN Systems. They didn't just contribute cash; they contributed know-how on the application and the system level to work with us. To iterate the product, to make the product better, to meet their high reliability standards.
No, I mean, it's extremely fascinating. Because I read our article at TCMC, they were also involved because 5G, because they make all the chips for the 5G units. And now it's coming full circle. I'm understanding that you guys working with them, and then now getting to the base stations for 5G, and gallium nitride is being one of the products being used and now being scaled. Being scaled at the price points coming down, it's getting better from a yielding standpoint.
It is, and since 2014, we've now shipped more than 20 million GaN transistors with very low field defects. We're proving the fit rate and the theory that we achieved in the reliability studies, and with that volume and increase in yields that comes along with volume. And that learning, we've now been able to ship. We have 3 products that are under $1. So GaN under $1 was a big milestone and achievement from us, and that's really what it allowed.
Getting down to
this kind of a consumer product, where every penny is scrutinized.
Consumer products. And I think we talked about all the industrial, EV, automotive. But consumer is very sensitive.
Consumer is very price sensitive. In automotive and some of these other applications that we talked about, they're a little less sensitive, but they're still extremely cost sensitive on everything.
Correct. It makes sense. But moving forward with that, so we are in this business. The last pandemic has really changed the supply chain and everything. It kind of broke it a little. It snapped. And now, right now, how is the overall business for you guys? I probably saw a little downturn, but how is business on the trend right now for you?
So actually, we didn't see any downturn because our technology is very disruptive. It's new, and we're growing faster than the market overall.
Oh, right, okay.
So that's been tremendous. And the pandemic, it definitely impacted some sectors more than others. If you can imagine anybody doing things for cruise ships, hotels, bars, entertainment venues. Those
service industry.
Those kind of companies have slowed down their R&D investment. It was difficult for some of the car makers because you don't just do everything in your home when you're working on a vehicle. That's a pretty big thing. So there's only so much you can take home with you. Yet other products like these didn't slow down. In fact, many of them accelerated. There was a huge boom in consumer electronics
from the work from home.
From work from home, everybody needed a laptop.
Correct.
And other infrastructure. And there was also a boom on stuff to keep the kids busy while you're working. So there was a boom on game stations and electronic toys and all kinds of, you see all kinds of electric scooters and stuff.
Oh, everything. Bikes, scooters, everything. Everything.
All that needs power electronics.
Yeah.
So some segments were up, some were down, and that drove some imbalance in the supply chain. Some companies a little bit, didn't know what to do. So the natural reaction is to hit the brakes on investment during a pandemic. But it turns out the thing to do was actually to accelerate through that, because with these 5 megatrends that we talked about, plus a few other adjacent ones, things like IoT and the space and even the medical segment excited a lot with respirators. Respirator parts were hard to get in the early part of the pandemic. Those trends were always there, and they were just maybe, no pun intended, they were masked a little bit by the pandemic. People took their eye off the ball, but those underlying trends are there, and you probably believe, like I think those trends are here with us to stay for the foreseeable future. Yeah,
it is. I mean, it's pushed us to evolve. Of course, I always tell people, like, we're moving for the future. The past is the past. Every day is a new day, and it's the last year has evolved us digitally, especially digitally to, we've always had technology of virtual and all this stuff, but it's been multiplied, magnified, that, hey, these are things, and things have got more efficient. I mean, come on, the interpersonal we've missing, but of course there are things that are a little more efficient because we figured out we can accomplish much more with not traveling so much, wasting so much time. But somehow during the pandemic, I mean, I probably, as for yourself, is we've even got busier, meaning like, even though we're not traveling, or I used to travel to Asia probably 3 times a year, and now I'm not traveling, but I'm even busier than I ever was before.
Yes, and I think one of the things that we noticed is in a lot of businesses, people being out of their office left them more time to think outside the box on their bigger, longer-term problems than solving the everyday challenges that come up in the office environment. And so there's maybe some renaissance of ideas that are coming out of this, where people got some uninterrupted time to really think and create and look at different ways of doing things. So we were busier than ever. And being a new technology, people finally had time to slow down and say, okay, let me really take a look at gallium nitride and how that would make my product better.
Yeah, I mean, it's true. So what is your perspective of right now, the supply chain break a little bit, lead times have gone out. I mean, how has it affected your guys' supply chain for lead times and things for gallium?
So we didn't get that. We're a little bit impacted indirectly. Okay. We work at TSMC, but we're on a process that's unique and growing, and they're making the investments for that. We're on 6-inch wafers, which is trailing edge for microprocessors and communications devices, which is nice because it's very low cost. And as those designs move on, it leaves more capacity for gallium nitride. But at the same time, the cycle times have extended a little bit. People aren't quite as efficient and working as they once were. And so that's the front end. We also have back end where you have to take the die, the wafers, slice them into die, put them in packages, and test them, and then ship them out to customers. So all of that, you can imagine, has also been impacted. So the back end lead times have gone out a little bit. And now with the crunch and the boom in demand, there's not a lot of upside capacity available. So it was incumbent upon us to have contracts and plans and long-term forecasts to secure that capacity, and we did a good job of that. But yeah, minor impacts. You can't just react quickly to changes to that forecast. So the forecast becomes very, very important. And how do you forecast during a pandemic? Who could have known all of this?
Who could have known? I mean, everything is thrown out there from the... I mean, who could have known the stock market would have been as high as it would have been through a pandemic? Who would have known that? Who would have known to double down on everything? And some people did. Some people took risks, and some people, as you said, pulled the brakes, and then they got left behind, and now they're trying to catch up, which is it's hard.
Exactly. Yeah. The automotive industry, I think, is widely known that they put the brakes on a lot of things, canceled backlog, didn't take the product in, and that was to the benefit of the consumer products that were booming. Everything just shifted over to supply that. And they still are in high demand. And now the automotive guys have come back on.
We need our capacity. Where's our
capacity?
Yeah.
So I think you're going to see that this year will be an unprecedented year of investment.
Yeah.
But of course, that takes 1 to 3 years, depending on what
to build
it is,
infrastructure.
to build the infrastructure, to qualify it, to get it into place, to where it's production and qualified. And so there is some lag on that investment. It's not immediately applicative, but well, I think the demand will be there to consume that all for the next 3 years with these 5 megatrends.
Yeah, I mean, from you being in the industry for, you having experience and wisdom through the different generations of technology, and now working, because of course with Infineon you work with, was Infineon also fabless as well?
No, Infineon very much have state-of-the-art manufacturing that they own. Mm-hmm. They're expanding throughout this. You can read that in the papers. And, they're one of the largest suppliers of power electronic in the world, and they do most of it in house. But they still to outsource some of it. You can't do all of it. Can't do all of it.
Contractors.
So hybrid.
The hybrid, the people out there is people keep talking about, because as I said, offshoring, onshoring with the TCMC, of course, is the majority power of all the wafers. They make majority of them. Also, there's UMC, there's Global Foundries here, but now all the companies are like kind of restructuring. Because how I look at perspective was, you want to focus on engineering. Companies like GaNs, you focus your things on engineering gallium, and then they subcontract a wafer, someone who's an expert at building wafers, at the technology, has the capacity. But now we see sometimes you put your eggs in all in one basket, and there's a supply chain break of demand spikes, which this pandemic has caused. And
not just pandemic. There's been some other unfortunate incidents.
Yeah, natural disasters.
The deep freeze in Texas has impacted
materials.
The supply chain
recently
on certain materials.
Fires in AKM factory. There was a fire in Renesas factory.
So all of those things take 3-4 months of production offline. Plus, you can imagine a fab is a very clean space. The air has to be purified. Any smoke that goes through there is a nightmare for a fab operator. It takes a lot of time to recover from that.
Oh yeah, because I spoke with David Loftus from now. He's the president of ECIA, but he used to be with Xilinx, and then he went to Analog Device and Maxim and all that. Which with Maxim, all the things that he was talking about. Yeah, everybody invested. It was heavily investment into the R&D, and they went fabless on everything because there was, at the end of the day, it's their companies that want to make more margin, so it makes more sense to everybody dive in, but everybody's kind of feeling some strain, so they're realizing they need to have different allocation. The supply chain globally needs to be more allocated to different parts of the world, not just in one territory. We should have different areas just in case a natural disaster happens, a fire happens, a tornado, an earthquake, that they can switch over offline and build up a capacity on the other end. That's why our administration has, gone through, the new administration has put in these things to build, to give, subsidies and build in Texas, Austin, Samsung, Intel, TSMC.
TSMC is for the first time investing outside of Taiwan, and my understanding, they're rumored to be going to build a plant in the U.S.
Yes. So everybody's coming in to build in the U.S. because we have to supply, and that's the thing is, as we grow and coming from the I would say 2000s, just like you brought up, the dot-com area where everything was digital and e-commerce came on, everything came online. It was a big boom. There was a big boom, Y2K, that big boom. And then we went actually into, it could jump down the technology. Then we went to a housing, real estate, and then it came down again, and Great Recession. But right now, I think we're in a technology, industrial revolution of digitalization and technology and engineering and everything being connected that I don't see a downside for many years to come, because it's only going to go up.
I've been doing this for more than 30 years, and I couldn't agree with you more. I've never seen where there's this many things all growing at the same time, driving the demand for semiconductors.
I mean, it's people ask, or friends are not in industry, it's like, oh, why is there shortages, or why is this happening? I'm like, well, you don't understand that. Just look at that car. Car maybe back in 10 years ago, maybe use a couple microprocessors, and it has control units and sensors. Today, there's probably 100 sensors, or even more. Every sensor needs a microcontroller.
The sensors, we've gotten lazy. We can't just roll down the window with a hand crank anymore. There's buttons. And your seat has 100 different adjustments, and the lift gates are automated. All of that takes electronics. A lot of that is power electronics.
Yes.
So in a regular combustion engine car, there's $300-400 worth of electronics in that today. With an EV, that adds another $300 or $400 on top of it. So it doubles the electronic content in the vehicle. When you talk about ADAS, which we haven't even talked about, that's another mega trend, the autonomous drive and safety standards that are coming. That's another $300-400 of sensors and LiDAR and things like that that will add semiconductor content to a vehicle.
Yeah, which actually a good thing. I want to talk about the autonomous driving, which is about LiDAR. What is your perspective between LiDAR technology and the scale of it? And
so LiDAR, radar, cameras, cameras working together seems to be the most fail-safe solution because you need to see through fog, through rain, through snow. You need to see around buses that are at a corner to see if somebody's going to step out. All of those kind of real-world situations, you can't just rely on one. So having all three of them and the compute power to combine those all, I think, is a key enabler that I see going forward. Where GaN participates is on the LiDARs today.
Okay.
GaN switch very fast. We can switch at 100 megahertz if need.
Oh, wow.
They don't need to go quite that fast in a LiDAR system, but the faster switching and the more pulses you can get, the more pings.
The faster.
You can transmit more power, you get a further distance reading. So if you're driving at, 50, 60, 80 miles an hour down the road, you can imagine the further out in distance you can gather information, and the more information you get, the better decision you can make as to when to hit the brakes and do that kind of thing. So GaN is going into those forward-looking LiDARs. It's maybe not being used in all the little ones that, when you're backing up and it's beeping
backup sensors.
You don't want to run into the car behind you. That you don't need it so much.
But for more safety, as you would say, the safety side is where, safety, high speed. I just said, like, even probably your car or my car has those sensors where there's a brake, like it will brake for you if you put the brake assistance on.
Yeah.
These are things that
keep you from going out of the
lane or notify you from going out of the lane. It's getting smarter and smarter. And that data, again, going back to Tesla is, one thing Tesla has is its data. They have the most data in the world. Billions of miles of people's data.
So this is a great example about how things are becoming interconnected. You have all the real world power problems that we discussed, but the car now is becoming a huge source of information on roads and traffic and conditions. All that data is going into data centers and being crunched and going into AIs to make decisions with. So this kind of stuff, this is a trend that's here for the future.
Yeah, the multiple AIs. I had Keith Stryer on a couple weeks ago from his VP of AI initiatives at NVIDIA, and he was talking about the multiple AIs. Everything's is going to be AI based, and computing power today is they're building platforms for all. NVIDIA is now, instead of being just a gaming company, they build a platform base for developers to build on top of it for computing and how computing is going. But AI overall is like there's multiple AIs working in, say, a vehicle, multiple AIs working in a system.
Yeah, there's some that are working on the edge.
On the edge systems.
In the real world where it's got to make an instantaneous decision, doesn't have time to go even over 5G to a centralized computer to crunch all that data. That happens later, but the decisions need to be made on the edge.
Too. And that's that computing power needs to be there. Of course, the power to power it efficiently, to power it, the fast switching off of that, and to think and make decisions is getting. It's fascinating getting into that. For the AI world, we're just on the cusp of that. Even though AI has been around for many, I think in the last starting from mid 2000s, but really it's quantified itself year over year of how much AI is coming into the Internet of Things. People around IoT, Internet of Things is basically AI based because there's a lot of data and it connects to another brain in the sky, as you call it, the cloud. There's a brain, and those things, and they learn. It's a learning system, continuously learning, and the humans are building an infrastructure for smart computing systems, and it's so fascinating how all this wraps around. And GaN's being one of the Gallium Nitride and GaN System company itself is part of that. To really advance technology moving forward. And that's one thing that I was so interested to having you come in and share those insights. It's so fascinating, and especially with the new generation coming in to really understand. If you're not, one thing is I kind of feel like need more engineers out there. We're a new generation of engineers coming in.
I can tell you firsthand that the world has a shortage of power electronics engineers. If you have knowledge in that area, there's plenty of jobs. You can pick and choose from which company because everybody is working on things. So we mentioned all these trends. Everybody needs power engineers, and it's not always been the sexiest thing to do. It's not the first on people's mind. But when you really think about what, it's solving some technical challenges, but it's also solving global problems, climate change and things like that. And so there's a part of me that feels pretty good every day waking up, hey, we're selling product and that's our goal at the end of the day. But it's not just a transistor solution. It's solving real world problems. It's helping to solve climate change, 1 watt at a time, 1 percent at a time, one customer at a time. All of that adds up.
Yeah, and it's changing the world. And you bring that up is, hardware, we've been in the industry, our business, our family has been in the industries for 40 years. We've been in the industry of hardware, of components, and it's not been the most sexiest because software has come. Software has taken over that. But now with advanced technology, the hardware has become more sexy because just like you're involved with these, you can be a power supply engineer or a power MOSFET engineer or something, but you get to work with these top companies in the world that are innovators and they're using platforms and you're hands-on. It's not like, we're in a GaN Systems. As GaN Systems is working with leading technology software companies around the world. That's exciting. And you get in that experience and knowledge and wisdom and that you're changing the world is mind-blowing.
Yep. And we're helping to. It takes a team to do that. Everybody thinking and working together, from the fab to the designers of the different transistors. So,
these are all the little transistors on here. Yeah. I mean,
that's what they look like. To the application experts, all the biggest companies in the world are concerned about power consumption and making their products smaller, lighter, more efficient. And so naturally they're talking to us. And that's a great place to be because we get exposed to a lot of different ideas.
It's funny because my father was a power supply engineer in the 70s. And he worked here all local because a lot of power supply companies here in Orange County or Southern California in the 70s, 80s, and 90s before they transferred to the Far East for manufacturing. And he was a power supply engineer. And he's like, and still to today, he's like, at the end of the day, everything needs power. Doesn't matter what we think. Everything needs power.
I think a lot of people maybe take it for granted, but you look around just in your own home and your office and your car at all the power switches and things that are electrified nowadays, and it becomes apparent that this is it's touching everybody, maybe not consciously, and there's a lot of ways that we can do better. I mean, your refrigerator. Think about that. The energy consumption in the world today, data centers maybe 2%, but it's rapidly going to grow to 10% of the overall consumption. The biggest consumption is in electric motors, somewhere 50 to 55% of the energy consumed is electric motors, and that's keeping the building cool, keeping your food cold. Your refrigerator runs 24/7, 365, and refrigeration alone is 15% of the global energy consumption. If you can save 30% off of that by going to a smarter power semiconductor, everybody benefits. But there's resistance to change sometimes. It takes a little bit of investment,
there's a lot of
knowledge.
Big people and big companies power because, of course, going to EV, there's a lot of, I would say politics involved in that as well with oil companies and things involved. So there is a lot of pushback on some things of but scaling and but going back to your point is like smart grid systems.
Yep.
Homes, everything's smart. They use power. They efficiently transfer power correctly, using every house being connected with power, and they can use each other's power and as a source. So these are the fascinating things that's here for the future. That's really for me is that its future is infinite. What we're going into, the power is infinite, and I am only optimistic of what's in for the future.
So I've been very blessed and excited to be in this segment, learning from the best minds and the best companies in the world, and applying this and seeing that it's not just a single shot trend. It's a trend that's here to stay and will continue to grow across all of these segments. And so that's a fun place to be.
Well, awesome. Well, wrap this up. Can you share some words for really what's in the future for GaNs? Where do you see GaNs going first? Where do you see what's your guys' trajectory next 3 to 5 years for GaNs?
That's a good question. So first of all, we make 650 volt and 100 volt transistors today. We've had to extend them up and the power that they can handle at those voltages, and as well make smaller, more cost-effective ones so that you have the right component, whether you're doing a laptop phone charger or you're making an EV. Additionally, we'll fill out different voltage ratings, 200 volts coming. There's talk of 900 volt, 1200 volt coming. And traditionally, that's been the space of silicon IGBTs and silicon carbide. And so you're going to start to see that there's more options coming in the future from GaN in that standpoint. And then just continuous improvement in terms of the RDS on and the switching losses will continue to improve. Through the natural evolution. We're still on the curved part of the learning curve. There's a lot of learning still to come.
Oh, wow. I mean, it's so fascinating. But then comes again, so what's your thoughts and opinions or message for the younger generation getting into this industry?
So again, if you want something that's exciting, that's a wave in the future, that's going to help make a difference in a lot of different areas. We talked about the 5 mega trends in consumer and data center and 5G, in the electric vehicles and in the alternative energy space. There's an abundance of opportunity out there. It's an exciting place to be, and it's one where you see a lot of cooperation. Even some of my gallium nitride competitors out there, we kind of silently root for each other because we know it's doing a bigger good, and we know it's helping.
Yeah, it's helping the world, changing the world, one transistor at a time.
One transistor at a time, 1 watt at a time.
1 watt at a time.
1 watt at a time.
Well, Rick, it's been so fascinating. Thank you for coming here. I would love to, future as things change, to have you back on, as the words of wisdom and the experience that you have is priceless. And I really appreciate you coming, sharing your knowledge with us on the Real Talk, and really going over, getting kind of deep into what really Gallium is and GaN Systems and what you guys do and how you guys are also changing the world in that. So I appreciate it. Thank you very much.
Well, thanks a lot, Rob. Appreciate being here, and thanks for having me.
Pleasure. Thank you.